All right, we're going to keep talking about integration in this video, but instead of focusing on definite integrals or the general idea of what an antiderivative function is or anything like that, even the link between them, we have all that for now. What we'd like to do is focus specifically on one sort of strategy for finding antiderivatives of functions when it's a little bit more difficult than normal. We have some basic antiderivative rules for what we'll call like elementary functions, right? Power functions and trig functions and exponentials and blah, blah, blah. We know how to find antiderivatives of most of those. We don't have all of them yet, but we have most of those things. What we're going to do now is focus instead on undoing one of the more advanced or in-depth or involved differentiation rules, chain rule. So our goal here is going to be to find an antiderivative by undoing the chain rule. If we can recreate the chain rule, but just do the differentiation, then hopefully in that example we'll see that we can go backwards through it, and we'll see a general process there. We'll build a nice formal structure and strategy for it, and then at the end we'll also talk about some general intuition for what we're actually doing with this integration by substitution method. So that's what we're going to focus on. Let's get this thing started. Again, we want to start this off with a quick recap of how does the chain rule work, right? We're doing this backwards version of the chain rule, undoing the chain rule. So let's remind ourselves on how the chain rule works. There's informal and formal ways of doing this. I'm going to do the actual substitution here. I'm going to say, let's call this inside part U. And hopefully by now we're all pretty good at recognizing what the inside layer of composition is. So we'll say U is equal to 3x to the 4 plus 1. And then we know we're going to need the derivative of that thing with regard to x, and that's 12x cubed. Perfect. I don't remember how I've been doing this with my colors, so I'm just going to kind of wing it here. We know that the derivative with regard to x of u to the sixth here is really going to be the derivative of u to the sixth with regard to u times the derivative of u with regard to x. So we just need to make sure we link these derivatives together, right? Differentiate with regard to u, and then differentiate u with regard to x, and that should be fine. All right, so the derivative of u to the sixth, that part should be pretty easy. We've got 6 u to the 5, and then we know what the derivative of u is. That's 12x cubed. Now what we can do is take this 3x to the 4 plus 1, put that in place for u, and we have 6 times 3x to the 4 plus 1 raised to the 5th power times 12x cubed. I'll probably just write this as 72x cubed times 3x to the 4 plus 1 raised to the 5th. There's chain rule. That's how that goes. Hopefully we remember. If you used things like boxes and box prime or whatever to do this, then hopefully you can see like there's your inside stuff. That's the derivative of the inside. Everything works out pretty well. Again, remind yourself on how the chain rule works. If you need to pause the video and go back and look at some things, no problem. Okay, so let's think about undoing the chain rule. We'll just think about this in general first, then we're going to take a look at that specific example again. Okay, so what are we looking for? Chain rule deals with composition, so obviously we're looking for composition, right? But we're also looking for function and derivative pairs. What do I mean by that? Well, let's look at our answer here, specifically this second to last line. We can see that there's a function, 3x to the 4 plus 1, and its derivative, 12x cubed, in this answer. And so if we're going to be going backwards here, we need to look for this pairing, right? So this is really like the u and the du over dx, right? Where what we were differentiating was like g of u, and so we had some sort of like a g prime of u times u prime of x. So some sort of a function u and its derivative u prime pair. Then what we also need is some sort of a structure for anti-differentiating the outside function, this g prime thing, while dealing with that extra derivative at the end, that u prime. So that's where the structure, the process that we're going to build is going to come in, and it's not a big deal at all. What do? The exact kind of variable substitution that we did for the chain rule, except we're going to be using an integral form of it instead of a differentiation form. So let me talk with you through how this works. We're going to be thinking about chain rule, and so if we're doing a variable substitution, we're still going to pick the same inside function. Our intuition here is going to still be good, which is helpful for us. We're still going to say u is equal to 3x to the 4 plus 1. But instead of saying du over dx is equal to 12x cubed, what we're going to do is notice, oh, wait a second, we're looking at integration, meaning we need a differential on the outside of our integral, right? We have this dx, and remember we talked about what that dx means. One of the things that it means is that like, oh, this is the end of our integral, right? What it also means, though, is that we're anti-differentiating with regard to x, right? The x is telling us what variable we're integrating with regard to here. So if we're going to do a variable substitution, we need to change our differential as well. So instead of saying du over dx equals 12x cubed, we're just going to define the differential du. There are several ways of doing this. You can think of du over dx and just multiply both sides by dx. Or what you can do is use the definition of differentials that we've learned and talked about briefly and say du is really u prime times dx. This goes back to all the linear approximation stuff and blah, blah, blah. And then we can say, all right, I know what u prime is. That's 12x cubed. Perfect. So we have a u here. We've got a differential du. Now, again, there's lots of ways of doing this substitution. I'll just talk about how I'm going to do it. I'm going to rewrite this integral a little bit more explicitly just for us so we can see there's our u, because remember we said u was equal to 3x to the 4 plus 1. And du we said was 12x cubed dx. And here it is right here. Oops, du. There we go. So I'm going to go ahead and just do the substitution. I'm going to swap these things out. So this 3x to the 4 plus 1 is going to disappear, and it's going to become u. And in our mind, we really know that that's what we're saying. When we say 6 times u to the 5, we really know we're saying 3x to the 4 plus 1 raised to the 5th. And then instead of writing 12x cubed dx, we're just going to write du here. These integrals are equivalent to each other under this substitution. They are the exact same thing. But it should be easy to see that one of these is much easier to anti-differentiate, right? This one in red that I've got written, if we notice that du at the end is really telling us that u is the input variable that we're anti-differentiating with regard to, then suddenly we can just treat this integral normally like some sort of regular power function. Add 1 to the exponent, divide by that value, so we have 6u to the 6 over 6, or this is u to the 6 plus c. Done. Now, to be fair, our original stuff was all written in terms of x, so let's go ahead and do our substitution back, and we have 3x to the 4 plus 1 raised to the 6th plus c. And hopefully this makes sense, right? When we were doing our example, we started with this. We could have added or subtracted a constant on there, and we know it wouldn't have changed much anyways. So this works out pretty nicely for us. This process that we have of doing this variable substitution hopefully is helpful. Remember, we're looking for an inside function and a derivative pair. And here we had to split things up a little bit. We had to take this 72x cubed and write it as 6 times 12x cubed. That way we could find this derivative pair. We're going to get lots more practice with this, but for now, let's just remind ourselves about the formal process. So we're going to have some integral in this form. This looks really clunky, right? But what we're going to notice is that here we have some u function, and here we have some differential du that we're defining. So we have this integral that looks really complicated, but we're going to be able to substitute things out, right? Find the inside function, find the derivative of it. We might need to do a little bit of work here. This part is going to maybe give us some trouble, and we'll focus on that in extra videos later on. We do the substitution, right? Label them like we did earlier and swap them out. So instead of f of gx times g prime of x dx, we've got f of u du. Once we get this integral, hopefully the key is that this one is easy. And again, we'll put like a little asterisk there because anti-differentiation is rarely easy. But hopefully this is one that's like a basic form, right? We had a power function here. That's, in the grand scheme of things, not a big deal. Then we go ahead and anti-differentiate and substitute back to the original variable x. This is a really common problem-solving technique, and I want to draw this out in hopefully a helpful way. So what we have over here is some integral that's living over here in our x world. And we could write it as f of gx and all that stuff, but I'm just going to write it as f of x. Who cares what it is? It's some function of x, right? And normally what we do is we say, oh, great, I can do that. I can find an antiderivative. And this is what we do. And if you can, great. Go ahead and do it. But sometimes we find that there's like a big roadblock in the way. And this is hard to do. It's not always easy to just find an antiderivative. And so what our problem-solving technique is we are going to do a nice variable substitution, and we're going to take our integral and translate it over to this u world instead. We're going to bring it on over here, and it's going to become some other function. I'll call it g of u du. This is our u substitution. We're going to define some u equals something, right? A du equals something, and we're going to drag this integral, translate it over into this u world. And the point is, we can find an antiderivative over here, and hopefully if we do this nicely, it's easy to do this. Now, not every u substitution makes your integral easy, but the good ones do. Right? We're always going to be looking to try and simplify our antidifferentiation process. And then once we have this antiderivative in terms of u, we're just going to use that same u substitution to write it back in terms of x. So that's what we just did in that last problem, right? We took this big convoluted multiplication of functions and we defined some u substitution that brought it over to this pretty easy 6u to the 5. Antidifferentiated that, and then threw our x substitution back in. This is a super common problem-solving technique in math. It gets used everywhere, not specifically with integration and stuff like that, but just in general, doing a nice variable change, solving a problem over in this easier context, and then bringing things back. This is a really common problem-solving technique pretty much everywhere. I always give an example of working on like a Rubik's Cube when I talk about this with my face-to-face classes. If you've ever played with a Rubik's Cube, you notice that they are difficult to solve because every time you want to fix some problem on it, you want to switch some blocks out or make a color match up with something else or whatever, every time you do that, you wreck some other portion of the cube. And so as you get further and further into solving this, you have a couple of faces or whatever, who knows, then whenever you try and change something to get further into solving it, you break what you've already done. And it's really difficult. And so you can learn a whole sequence of moves and an algorithm for working with this. But in general, all of the like moves that you do that are going to be helpful are this exact process. You take the things that you want to fix that are difficult to fix without breaking everything else, and you move it to some other corner of the cube, and you fix it over there. And then you undo those moves to bring them back. So if you've ever had some experience with Rubik's Cubes and you know some of the algorithms and things like that, hopefully you can see this process working there as well. This is, again, a super common problem-solving technique. Let's just take a look at one more example before we go. 7 sine to the 6th x cosine of x dx. We want to anti-differentiate this. Right off the bat, what I'm going to do is rewrite this for us. Sine to the 6th x, that really means sine of x raised to the 6th cosine x dx. What I want you to do is to pause the video and see if you can, from here, figure out the u substitution stuff. This shouldn't be too bad. Again, we're looking for composition of functions, and hopefully when I've rewritten this, we can see that composition a little bit better. We're also looking for function and derivative pairs. Hopefully you can see some of these nice trig functions connecting with each other. Tinker with a couple of u substitutions here. Pause the video, come back in a sec, and see what you've got. All right, let's pick this up. Hopefully you noticed, wait a second, sine of x, that is on the inside. Du then is going to be the derivative of sine of x, cosine x, times the differential dx. That's right here. So this stuff is u, and this stuff is du. If you haven't done the substitution yet, again, pause the video and go ahead and finish this problem out. It should be pretty easy from here. Right? Once you rewrite things, it shouldn't be too hard to do. Sometimes people get stuck on the rewriting, but give it a shot. All right, if you've done it already, here we go. This is 7 u to the 6th du. And again, we've just got a nice power function here. I know the antiderivative of 7u to the 6th. That's just u to the 7. 7u to the 7 over 7, whatever. Plus some sort of a constant. And now what we can do is toss our u equals sine of x back in place right here. So this is sine of x to the 7 plus c, or sine to the 7th of x plus c. Now, a good question that we can ask is, how do we check our answer? Well, we started off this video saying we're going to undo the chain rule, right? So if you want to check your answer, just differentiate this, and notice you're going to use the chain rule here. So use the chain rule, find the derivative of 7, or sine to the 7th of x, and you should get this. So that works out pretty nicely. Okay, so what we're going to do in the next couple videos is tinker with how we can apply this process when things aren't set up so nicely. They're not set up so perfectly where we can just see all the pieces really easily, do a clean substitution, and go from there. We'll take a look at how definite integrals work. We're going to take a look at how to tinker with the inside integrand function to make it set up correctly, and we'll hopefully build up some intuition from there. Get some practice on some of these basic examples before we move into some of those, just so we can really understand the idea of substitution, but hopefully that'll be helpful as we move on.